So next up, we have Stefan, who's going to be telling us about more energy-related modeling. And this relates to the parameter question. So I came to meet Stefan when he banged on my door and said, I'm trying to build very big JuMP models with parameters, and it's not working. What should I do? And so the person to talk about parameters is Stefan.
Thank you. Nice. Perfect. It works. Let me just quickly pull it up into full screen. All right. There we go. So, yeah, thank you and welcome to my talk. I'm not going to share any results today. I'm more going to be talking about what we learned and what we didn't learn during our journey with JuMP. And so a quick start. Give me a second. There we are. So what am I going to talk today is TESCA, our techno-economic system and component analysis framework, and specifically TESCA Optimizer, which is the optimization tool behind it. So preface, TESCA Optimizer will hopefully be open source soon. We're talking about this for a couple of years now, but will be soon in the future. So I want to begin with what it is and some of the key facts. Yes, it's an energy system optimization framework, but the interesting part is that we're using it for vast different models. So we're using it for low latency model predictive control, meaning there's a few milliseconds to solve each model, where it's about milliseconds to rebuild the models. But we're also using it for continental scope models, where we take pure LPs that take hours to days to really solve. So we replaced a lot of different tools, but this one single thing here. And so what are some of the features? One of the most important ones that we're proud of is that we are able to describe arbitrary energy system models using YAML and CSV files. So there's no coding involved. And even if you want to create new energy carriers, if you want to create new types of devices in your system, you can create those devices using YAML files. And why is that possible? And that's probably our biggest achievement, is a kind of abstract block structure that we use. So we're not talking in energy system components, but we're talking in abstract building blocks. And you can take these different building blocks to combine them into bigger things. So for example, you could use them to define a heat pump in a small household, but you can also use them to define a large-scale nuclear power plant. And why is that important and why is that interesting? And that is mainly due to the next fact that we can define various things, like, for example, decomposition approaches, stochastic optimization, or other cool things like time series aggregation on these abstract building blocks. And then they immediately scale to any kind of component that the user wants to define. So you don't have to do decomposition approaches again for different types of energy system components. We have them built into the abstract core blocks. So, but onto our learnings. And I want to start with why we're using JuMP. And preface, we were really not happy with using JuMP when we started out in 2021, because there were a lot of hurdles to overcome coming from a super object-oriented programming style and thinking about models and then transferring that to JuMP. But the thing is, JuMP was way too fast in 2021 compared to other alternatives, so we had to use it. And now in the end, we're really happy that we chose it, because the thing is that with the performance comes the possibility to slim down our code base. I've just checked, so all of what I'm talking about today, we have around 10,000 lines of code, which is really, really small for an energy system model. And that is only because we can forego some of the optimization in the code base, some of the performance in the code base, because JuMP itself is so fast. And I want to point out two things. We heard something about relax with penalty already today. So the two things that happened really for us was, the first thing was a large problem with garbage collection in the string names that we had. And now there is the set string names on creation function that you can use to globally disable string names. So you can build readable JuMP models while still then having the full performance at hand if you actually need it. And the second one is the relax with penalty, and that's fairly new, if I remember correctly. And so the thing is, we had soft constraints from the beginning on. That was one of the crucial points of our model, that we enable our users to use soft constraints. And then the relax with penalty function came out, and that is a performance loss. So our manual implementation of that was a bit faster, but the thing is, it convoluted the code and it was really not readable. And relax with penalty is an easy approach to relax your constraints with penalty in the objective function. And so we essentially refactored our whole code base to rework that to use relax with penalty, because in the end, it makes it easier to maintain the code base, easier to read, and easier for other people to get into it. So it's really cool to see, like, the last 2.5 years, how much JuMP has developed and how much there is to actually use for us as model developers. So it's not just a framework, but it's really something that you can really use. We heard about the parameters, so I'm probably going to be specific about this here. So one of my biggest interests is always left-hand side, so multiplicative parameters. And the reason for that is I mentioned low latency model predictive control, for example, and it's really important that you can efficiently modify your optimization problem if you're doing iterative solves. And this is something that's really not possible in JuMP. Yes, of course it's possible. We have different solutions, but the problem is JuMP is so fast that you don't want to really slow it down with some slower thing. And so a lot of the different possibilities to include parameters kind of leads to quadratic expressions in some way or the other, because in the end you have to keep variable coefficients and you have to keep parameters. And so it's slower than you would actually like it to be. Maybe that's part for future contributions. We have a new one in the pipeline we call sparse expressions. Let's see, it's probably going to fail too, like the other ones before, but we're still trying. And other things would be like, for example, SOS1 and SOS2 reformulations. I've seen that there was some interest in the past regarding that. Maybe that's something that we can contribute as soon as Task Optimizer is actually open source. And the Techify JL, I'm going to cover that later on. All right, and I promised some learnings. So if you're interested in parameters, talk to me later because I can talk hours about parameters, but learnings. So thing one is memory usage. Memory usage is something that's strange because coming from other energy system modeling tools, you don't care about memory. It's all about performance, about timing. You really run out of time building large-scale models. You don't run out of memory. But now the problem is, like, JuMP is performant enough that you actually start running out of memory before you hit timing limits. So other models, they can't build on my laptop in a reasonable amount of time. JuMP can really do that, but now I'm running out of memory here. And so this is one of my personal interests and active research as a PhD student, is how we can actually apply various tricks, for example, decomposition, that like most people here probably know, but are really underused in energy system research, to achieve some kind of trade-off between performance and memory usage that actually allows people not familiar with these topics to actually just use it as a tool. Second learning, and maybe that's the most important one here, is usability first. So we're building a tool, we're building an energy system model, but it means there are actual people using that to create models. So we're not doing everything our own, so there will be users. And the thing is, users will not always be developers. To be fair, most of them are not developers. They may not even come from a technical background, but they're used to tools that just work. And the thing is here, maybe your tool that you're building is way cooler than the tool they're using. Maybe their tool is even bad, but they don't care because their tool works. So you have to produce a tool that actually just works. And so how do we deal with this? First thing I already mentioned is the no-code approach. You can do everything using YAML and CSV files. The second one is graphical user interfaces. That's super helpful because that draws people into your tool. Next one is probably not the right conference to mention it, but you actually need a Python wrapper, and you need to communicate people what it means to use a Julia tool in the back end. Yes, we have the time to first solve that's really improving, but it's something different, and you need to communicate that to build trust. Trust will be my learning number 3. But regarding the graphical user interface, I've inserted a short plot here because I heard that there's some interest in that yesterday. So what we can actually do is, I don't know if you know Draw.io, diagrams.net, whatever it's called right now. So we have a possibility that the user can draw arbitrary diagrams, like can insert text and new figures and whatever. We can hide all of that. Just pick the stuff that we're interested in. We can actually convert this here into a full energy system model. And this is really cool because you don't need to write YAML files anymore. No coding, no YAML files, just drawing diagrams. And onto my last slide. So trust and correctness. One of the biggest problems with that is always how can we test optimization models? How can we ensure that they're correct? And I want to highlight one of the most important ones, and that is Techify. And we are really proud of that. That is that we can convert arbitrary JuMP models into LaTeX code. And this is really cool. You can see here that some of this is getting lost. So for example, here's Slack, with a question mark. That is a variable inserted by relax with penalty. So we are losing information here. But in the end, you can still see that's a lot cooler than doing a print of a few thousand constraints, because we can actually figure out how the mathematical description could look like. All right. Thanks. And any questions then later on.